All right, 5.3 diagonalization. So let's look at the notes. So diagonal matrix is a square matrix that is zero everywhere except possibly along the diagonal. Right. So we have a quick example here: a 0, 0, 0, 2, 0, 0, 0, 5. Right. So a diagonal matrix is also a triangular matrix. Right. A triangular matrix is whether you have all zeros below or above the diagonal. But in this case, we have what we call also called a double triangular matrix because it's all zeros above and below the diagonal. And what's so nice about a diagonal matrix, it's easy to find the power of a matrix, right? So let's say I have a cube, that means a times a times a. Now, usually matrix multiplication can take some time, but if you have a diagonal matrix, it's actually pretty easy to find the powers of the matrix, right? So basically, you just take all the diagonal and raise it to the same power, right? And everywhere else is still zero, right? That's it. Very easy, right? And that's one of the nice things about diagonal matrix. All right, so let's look at the definition. A square matrix A is said to be diagonalized if A is similar to a diagonal matrix. That is, if A is equal to P inverse P, dP for some invertible matrix P and some diagonal matrix D. Right? So let's do this. So A is similar to D, where D is a diagonal matrix. That is, A can be written as P inverse D times P, right? Where P is some invertible matrix and D is diagonal, right? Then we say that A is diagonalizable, right? So one thing with a matrix A is not all matrix will be diagonalizable, right? In some cases we cannot find any D or P such that A is equal to this, right? So there's a nice property to that. All right, let's look at theorem 5. Theorem 5, an n by n matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. In fact, A equal to P inverse dP with D diagonal matrix if and only if the columns of P are linearly independent eigenvectors, right? So this is one nice theorem, one nice part, right? So the columns of P are your eigenvectors, are linearly independent eigenvectors. In fact, the diagonal entries of D are eigenvalues of A that corresponds respectively to the eigenvectors of P. Right? So once you have this equation, A equal to P inverse dP, we are able to find all the eigenvalues and all the eigenvectors. All right, so let's take a look at example 2. Example 2, we are assuming, right, suppose A can be written in this form, right, PD, P inverse. So here A is actually what we call diagonalizable because D is a diagonal matrix, right? And then we have P and P inverse here. All right, so let's look at the first. We want to find A to the power of K for arbitrary positive integer K, right? So A to the power of K means we want to multiply A by itself K times. And by what we're given here, A to the K, I can also write it as P dP inverse multiplied by itself K times, right? So this is the fun part, right? Let's see what we have when we expand this. Right, so I have P dP inverse, and then multiplied by P dP inverse, multiplied by P dP inverse, dot, 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 P dP inverse, right? And what you're going to notice is that between every factor, we always get a pair of P inverse and P, which gives us the identity matrix, right? So if we simplify this, we actually would get P D D D. That doesn't look like a D. P D D D dot, 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 dot. D, and then P, the last P inverse right here, right? So exactly how many D's do we have here? We have KD's, right? So that is equal to P D to the kth power multiplied by P inverse, right? And this D to the kth power is very easy to find because D is a diagonal matrix, right? So to find the power of K for the matrix D, all we need to do is take all the diagonal entries and raise them to the kth power, right? Which would look like this. P multiplied by 2 to the k, 0, 0, and 1 to the kth power is still ones, but let me write down 1 to the k, and then P inverse. And then you can multiply these out, and then you will get a form for a to the power of k. All right, let's look at part 2. Find eigenvalues of A and the basis for each eigenspace. Now that's very easy. We don't need to do any extra work. First, we know that A is similar to D. That means they have the same eigenvalues. Okay, and D is a diagonal matrix, and more importantly, it's triangular, right? So the eigenvalues for D will just be its diagonal entries, 2 and 1, and those are also the eigenvalues for A. Right, so that's done. Now next, we need to find the basis for eigenspace, right? Basis for eigenspace. Right, and then if you recall back to theorem 5, we know that the columns of P are linearly independent eigenvectors, right? So P is the matrix 3, 4, 1, 1, right? So each of these columns is going to be linearly independent eigenvectors, right? So the basis would just be the collection of these two vectors, 3, 1, and 4, 1. Done, right? Nothing extra we need to do. All we're doing here is using theorem 5 to help us find the eigenvalues and the eigenvectors. And of course, in this case, the basis for the eigenspace. All right, and for example 3, go ahead and try this one on your own. It's the same thing, right? Look for the eigenvalues, which is you can look at the entries of the diagonal matrix D, and then for the linearly independent eigenvectors, you look at the columns of P. Right. So the diagonal entries of D 5, 5, and 4. So 5 and 4, they are your eigenvalues, and the eigenvectors will just be your columns, right? -2, 0, 1, 0, 1, 0, -1, 2, 0. Right? So pretty easy, nothing too tricky. So here are the 4 steps that you need to diagonalize any unbounded matrix A. First is to find the eigenvalues of A, right, using the characteristic equation. Find unlinearly independent eigenvectors of A. So once you have the eigenvalues, we can find the eigenvectors. Construct P from vectors in step 2, right? Once you get the linearly independent vectors, put them in matrix form, and then you'll get P, and then use the eigenvalues to construct your diagonal matrix D. And next, in example 4, we're going to perform these 4 steps together. Okay, example 4, part 1, we have a 2 by 2 matrix. So first step, let's find the eigenvalues of A. Find lambdas. All right, to find eigenvalues, you just find the determinant of A minus lambda I. So again, just subtract the lambda. All right, so here we have the determinant is actually just 5 minus lambda squared is equal to 0, right? So we get that lambda is 5. And in this case, we actually get 5 twice, right? The eigenvalue 5, we get it twice. All right, so next, let's find the eigenvectors of A. All right, so we get this by plugging lambda equal to 5 into here. Now we get this little matrix here, but here what we get is that x2 is equal to 0, right, from here. So x2 has to be 0, x1 is a free variable. So x1 has a general form of 1, 0, right? Oh, sorry, no, not this. All right, so the general eigenvector, right? So v1 has this form of x1 multiplied by 1, 0. Right, since this is the only eigenvector we can see, anything else would be linearly dependent to this. Right, so we can only find one eigenvector. Well, of course, we can find more, but they are not going to be linearly independent. Right, so in this case, since we cannot find two linearly independent eigenvectors, we say that A is not diagonalizable. Right? All right. Well, for example 2, this is our matrix, and actually there is some extra information. One information we know is that one of the eigenvalue is 5, and one of the eigenvector is -2, 1, and 2. All right, but these two don't necessarily correspond to each other. All right, so let's check how we can find the rest of the eigenvectors and eigenvalues. All right, so first we want to find the eigenvalues that corresponds to v1. All right, so for v1, we're just going to multiply the matrix A by v1, and then we get this. All right, so when you multiply, we get 6. Oops. We get 6, -3, -6. Right? And notice the relationship between these two, right? If you multiply this by -3, and you get that, right? So we can write this as -3 times v1. Then here, lambda 1 is going to be -3, which corresponds to this eigenvector. All right, so next, let's look at, try to find the eigenvectors for lambda equal to 5. All right, so let's do a new page. For lambda equal to 5, we need to first look at a minus 5i, right? Which looks like this: -12, -16, 4, 6, 8, -2, 12, 16, -4, right? And then if you look at set that equal to 0 and reduce it, right? So the augmented matrix, right? Set that equal to 0, and then if you reduce it, you get this right here. All right, so let's write out our first equation. I have x1 plus 4/3 x2 minus 1/3 x3 is equal to 0. Okay, so here we actually have two free variables, x2 and x3. So let's say if x2 is 1, x3 is 0, then x would have to be -4/3, right? That's the first. And another one, let's say x2 is 0 and x3 is 1, then x1 would have to be 1/3, right? And these two are actually linearly independent, right? But we can actually make this a little nicer, right? Rescale it, right? So maybe the first one multiplied by 3, I get negative 4, 3, 0, and then multiply by 3 as well, 1, 0, 3. Right? So that's a nice basis for our eigenspace. Right? So we actually get two linearly independent eigenvectors, and combining with our first one, we can get, so v1 from earlier, we know it's negative 2, 1, and 2. And then we have v2, negative 4, 3, 0, and then v3 is 1, 0, 3. Right? And then putting all three of these together, we can get our matrix P, which is negative 2, 1, 2, negative 4, 3, 0, 1, 0, 3. Okay. All right. So this first vector corresponds to the eigenvalue of negative 3, and the last two corresponds to the eigenvalue of 5. Right. So from this, we can construct our diagonal matrix D. So first is negative 3, right? And then the last two are 5. So 5, 5. And as you can see, what I'm doing here is basically putting all my eigenvalues on the diagonal corresponding to the eigenvectors in the matrix P. Okay, and this is how you can construct D and P using information given, like the eigenvalues and eigenvectors. Now, of course, this question is a little simpler because we are actually given the information that one of the eigenvalues is 5 and one of the eigenvectors is negative 2, 1, 2. But of course, you can try this from the beginning by looking for the determinant, right, of the characteristic equation. And then find the eigenvalues, right? But that will take you some time. But we will start with the homework with just some 2 by 2 to get you familiar with how you can work with this. All right, next we have some theorems to look over. Theorem 6, an n by n matrix with n distinct eigenvalues is diagonalizable. Right? So if you have an n by n matrix and then you found n distinct eigenvalues, then it's automatically diagonalizable. Now let's look at a little below theorem 6. When A is diagonalizable but has fewer than n distinct eigenvalues, meaning when you have repeated eigenvalues, it is still possible to build P in a way that makes P automatically invertible, as the next theorem shows. Okay, so we actually saw that in our previous example, example 2, right? Even though we have only 2 eigenvalues, but we were able to find 3 different eigenvectors that are linearly independent. Right, theorem 7, the A, B, and n by n matrix whose distinct eigenvalues are lambda 1 to lambda p. Right, for k between 1 and p, the dimension of the eigenspace for lambda k is less than or equal to the multiplicity of the eigenvalue lambda k. Okay, so let's take some time to look at this. All right, so suppose you have lambda 1 up to lambda p, right? And then in the middle, let's say we have some lambda k where k is between 1 and p, right? So let's just use some real number as example. Let's say I have some eigenvalue of 5 that has multiplicity of 3, right? That means the eigenvalue of 5 appears 3 times in here, right? So what this is saying is the dimension of the eigenspace will be less than or equal to 3. All right, let's look at the second one. The matrix A is diagonalizable if and only if the sum of the dimensions of the eigenspace equals n. And this happens if and only if, first, the characteristic polynomial factors completely into linear factors, and 2, the dimension of the eigenspace for each lambda k equals to the multiplicity of k. All right, so there are two things we need to be careful of. Yeah, the characteristic polynomial factors into linear factors, right? That means there's no repeating lambdas, right? And number two, the dimension of the eigenspace of lambda k equals to the multiplicity of lambda k, right? So like the previous example, if you have multiplicity of 3, that means we want our dimension of the eigenspace to be 3 as well. That means we want to find 3 linearly independent eigenvectors from the eigenvalue. All right, and the third one, if A is diagonalizable and B sub k is a basis for the eigenspace corresponding to lambda k for each k, right? So B is the eigenspace for each lambda, then the total collection of vectors in the set B1 to BP forms an eigenvector basis for Rn. Right? So basically, if you find all the eigenvectors for all the bases for all the lambdas, the eigenspace, and then you put everything together, then that will become a basis for Rn, because Ra is an n by n matrix, right? So basically, you put all the eigenvectors together, that becomes a basis for the entire Rn. All right, and some proposition, extra stuff from the theorem. Suppose T is an operator on V. Let lambda 1 to lambda m denote the distinct eigenvalues of T with matrix A. Then the following are equivalent. First, T has diagonal matrix with respect to some basis of V. Second, V has a basis consisting of eigenvectors of T. And the third one, dimension of V is equal to the sum of the dimension of the null space of all the different lambdas. All right, so the first point is saying T has a diagonal matrix with respect to some basis of V. All right, so that means T can be diagonalized by some matrix D, right? And D has the columns that have some relationship with the basis of V. Right? V again is the space. Right? 2, V has a basis consisting of the eigenvectors of T. Right? So let's say a basis of V is let's say m1, m2, right? Okay, and then that means these vectors are also the eigenvectors for T, right? That means T times m1 is equal to lambda 1 times m1. Right? All right, and the third one, the dimension of V is equal to the sum of all the dimension of null space of each eigenvalue. Right? So remember that the null space for A minus lambda 1, right? That gives you all the vectors that makes this 0, right? In this case, are eigenvectors, right? So we want to look at the dimension of all of them, right? Up to null A minus lambda m, right? So basically, what you can say is these eigenvectors, right? Let's say however many of them, that's going to be the dimension of V, right? And from here, we are just breaking it down by looking at each lambda and see how many eigenvectors we have corresponding to each lambda. And when we add everything together, that should have the same number of vectors as our basis for V. All right, so let's say if we have n vectors in here, let's say mn, then when we add up all the dimensions of the null space of each eigenspace, then we will get n as well, right? So there are n many of them. Okay, so these three are equivalent, right? If one is true, that means the other two will be true as well. All right, so that will be all. Thank you guys, and I'll see you next time.